We're going to start this chapter by explaining what kinetics are, and then I'm going to jump ahead a little bit to talk about collision theory, which is the theory basically undermining this whole chapter. So if we understand some of the basic concepts behind why reactions work, that will help to explain why the kinetics and the rates of our reactions are changing. So what is chemical kinetics? Kinetics studies the rate at which a chemical process occurs. Besides giving us information about the speed, kinetics also sheds light on the mechanism of a reaction, which really tells us how the reaction occurs. And if you're looking at making improvements or stopping a reaction, or you're getting a better understanding of why the reaction happens, that reaction mechanism is crucial to getting a better understanding of that reaction altogether. So kinetics always starts with measuring the reaction rate. So what is the rate of the reaction? Well, what we want to do is look at the change in concentration, or the delta concentration versus delta time. Again, delta always means final minus initial, so you're looking at concentration final minus concentration initial over time final minus time initial. So if we look at a very simplistic reaction where we have a bunch of red atoms changing into blue atoms, that now means you could measure this a bunch of different ways. You could measure the decrease in red atoms, you could measure the increase in blue atoms, and if you were to graph it, you would get a chart that looks like the one on the right. So what determines the speed? Why do reaction speeds change over time, right? Why aren't they consistent? So to talk about this, I want to jump to the near end of the chapter and talk about collision theory. So this is jumping ahead a little bit, but I think it helps to put some context into what we're talking about. Collision theory is an attempt to talk about the requirements for any reaction to occur. So we're going to be a bit vague here because we're talking about a huge range of reactions and what are the minimum requirements that all these reactions have. So first of all, collision theory assumes that in order for a reaction to occur, two different atoms or two different molecules have to collide. Right? And that collision ends up being really important because we have something that's known as an orientation factor. For example, if you look at this imaginary reaction at the bottom, what you'll see is that in order to have a successful reaction, two green atoms have to bump into each other at full speed in a way that causes these two green atoms to collide and stick together. If that green atom comes from a different side of the screen, if it comes from the top, comes to the bottom, or comes to the right, those two atoms will not run into each other, and they will not form a successful product, right? So what we're going to say is that the actual number of successful reactions you have are going to be very, very tiny. For most reactions, you're talking about millions of collisions in order to get a successful orientation and a successful collision. And now, in addition to orientation, we also have to have enough energy to make that bond stick, right? So we don't have to just bounce these atoms off to each other, but we have to kind of react to them in a way that their electron orbits fuse together to create a chemical bond. That is what we call the activation energy, the energy requirement for this new molecule, this new reaction to activate. So each of these things, the number of collisions, how difficult the orientation is, and the energy of those collisions all affect how quickly a reaction occurs. So we have this reaction coordinate drawing from Chemistry 151, and it basically says that reactants and products have different potential energy. And it's important to remember that when chemists talk about potential energy, they don't mean the physics definition, they mean bonding energy. So what we have is reactants and products have different bonds, and so therefore they have different bonding energy. Now what we focused on 151 is the difference between the reactant bonding energy and the product bonding energy. In this particular picture, reactants have more bonding energy and the products have less, and so that extra bonding energy that's not needed, it would be given away as the delta E or the delta H over the course of the reaction. This part right here. That's not what we're focusing on today, right? So that is the thermodynamics of the reaction, and we'll get to that next chapter. What we're focused on today is this barrier, this EA. And it turns out all chemical reactions have some kind of barrier that prevents the reactants from going to products. And that determines how fast this reaction goes. It's like if you're trying to
ride your bike over a hill, the height of the hill really has a huge impact on how quickly you can get from point A to point B. So, what does that mean in chemical terms? Well, we're not going to get too much into specific chemical reactions in this semester, but here's an example of an organic reaction just to give you an idea for what we're looking at. In this reaction below, we have the hydroxide ion attacking methyl bromide, or CH3Br. Now, as the OH minus donates its electrons onto the carbon bond, we create an unstable complex. This is a higher energy complex because it's put too many bonds around carbon. And so both of those bonds are unstable, right? We've designated that by drawing both as having a dashed line. These other lines, by the way, are just to denote three-dimensional depth. So these two dashed lines are unstable, and as a result, it takes a lot of energy to put together. And so what we end up with is a high energy, what we call an activated complex or a transition state, because it's a transition between the reactants and the products. So not every transition state complex will form products, but it's 50 to 50. So half of them will go forward, half of them will go backwards. But what that means is the faster a reaction creates this transition state, the faster and the more reactants will form products. And so understanding this transition state tells us a lot about how a reaction works. And we'll get to that in the second half of the chapter.
For example, if you look at the reaction between ozone and nitrogen monoxide, the energy of activation barrier is pretty small. As a result, this reaction is fairly fast. On the other hand, if you look at carbon monoxide and nitrogen dioxide, the EA barrier is quite a bit higher here at 134 kilojoules. And so this reaction is going to be quite a bit slower, even though the enthalpy difference is bigger. So the first thing you can do to make a reaction faster, on that note, is just give it more energy, right? If it's got to get over the top of that energy of activation barrier, more energy means higher, faster collisions, which means it's more likely to reach the top of that barrier. It's a bad analogy I sometimes use, but I often think of this as like you're trying to bike to school, and there's a giant hill in your way. The more energy you have when you hit that hill, the more likely you are to get to the top. The second way you can speed up any chemical reaction is by using more chemicals. Now, this is going to get more complicated in a second, but if you just think about it in the simplest possible universe, you're trying to get more collisions. The more molecules you have, the more collisions you'll get. In fact, we make the general assumption that if you double the number of reactant molecules of one type, so A is reacting with B, adding two A's means there's twice as many possible collisions. Adding two A's and two B's means there's 4 times as many collisions, and the reaction should speed up. So now here come the caveats. Right? The first is that solids and liquids do not affect rates. And this picture on the upper left shows a good reason as to why. First of all, solids can't move. Right? So solids cannot go out and instigate a collision, which collision theory requires. So they have to wait for the molecules to act on them. Secondly, most of this solid is not going to be exposed in the same way if you had a solid piece of metal, for example, it would not be exposed. And so only the surface area is really reacting at this point. Now, it's almost impossible for chemists to measure surface area of a particle, but what chemists will sometimes do if they have a reaction that's running slowly, and say they're using a piece of metal, is that they will powderize that metal. They will basically grind it down into nothing but powder and then run the reaction, and it tends to run a lot faster that way. Or you can agitate the powder. But still, that's not really an easy thing to measure. The simplest assumption to make is that solids don't affect reaction rates. Because again, it doesn't matter how much stuff you have, it matters how well it interacts. And again, it's not an easy thing to measure. Same thing for water or liquids in general. We talked in the last chapter about the sphere of hydration that forms around chemicals. Well, if you've got all this water reacting with this anion, for example, it doesn't matter how much water you add, it's already surrounded. So for that reason, liquids don't have a big effect either. The other explanation that is more mathematical but less clear cut, I think, conceptually, is that solids and liquids always have the same density. So we're really going to look at how concentration affects reaction rates. Well, the concentration of this solid is always the same no matter how big it is. The concentration of the solvent, of the liquid that's reacting, is always going to be the same. It has the same density at all times. So adding more of it doesn't change that concentration. So it also doesn't change reaction rates. On that final note, gases and solutes can change their concentration, right? Solutes in solution. And so as a result, we expect gases and solutes to have a direct impact on reaction rate. All right, so this last one doesn't involve collision theory at all, right? It's a totally different theory for how things react. But if we want to talk about real life circumstances, and I want to do that before we get too far, we have to bring up catalysts. Now, a catalyst is a chemical that is not consumed in the reaction, but makes the chemical reaction rate faster. So, a reaction that you're always around, you can't normally see it, is the decomposition of hydrogen peroxide. So if you buy a bottle of hydrogen peroxide at the store, it's usually 3%. It decays a little bit every day, and after 6 to 9 months, you basically don't have much hydrogen peroxide left. You really should buy a new bottle, is my understanding. But you can speed this reaction up dramatically by adding acid and by adding a halide ion, either bromide, iodide, or chloride. So it turns out that these chemicals are catalysts because they are not used at all. When you finish the reaction, you get out bromide and acid. But it gives this reaction a new pathway, a new set of intermediates that can form that take a lot less energy. So if you compare the slow reaction that you normally see with the reaction available when you add in this acid and this halide, all of a sudden this reaction occurs very, very quickly because it has about an eighth of the energy of activation barrier, right? So as a result, this happens very quickly. This is known as the elephant toothpaste reaction, where they basically add in soap to this reaction, and you can actually see all the oxygen bubble out of that soap very, very quickly. You can Google it. There's a million hits for elephant toothpaste reaction online. So real quickly, think of some ways that you can speed up this rusting of iron based on the following reaction and what we've already learned. So first of all, going in order, the first thing we talked about was heat. Adding heat speeds up almost any chemical reaction. There are some caveats to this and problems with this later on, but generally heat is going to speed these reactions up. The second is adding more gas or solute. In the case of this reaction, that would be O2. Adding O2 means more molecules moving around, more collisions, more successful products. It's a good reminder that iron won't make a difference. Iron is a solid. Adding more solid will increase the surface area, but it won't actually increase the speed of the reaction. It will just, it just still has to wait for those collisions on oxygen. Again, you could grind up this iron into a powder, and that would make this reaction faster. You could also put it in a solution and stir so that all that powder surface area gets to the surface, but we can't really measure those changes, right? We can't really say, oh, well, now we have twice as much surface area. So generally, it's just easier just to ignore the metal altogether. You could also look at this and say, oh, well, I know salt water causes iron to rust. I know acid causes iron to rust. Right? They talked about acid rain a lot in the 90s, for example, although most of you are too young for that. And sure, both those things will work. They are both catalysts. They are things that speed up this reaction that are actually not part of the reaction itself. Now, it's a little more complicated than that, and we will talk about that more in chapter 19. But for now, we'll say they're both catalysts. They're both things that cause this reaction to work without actually being consumed themselves. The last thing you can do is just leave iron in water. And what does that do? Well, most reactions work better in liquid, especially in water. because it gives a surface area, it gives a liquid medium for these solute to react with the surface. So we will talk about that a lot as we move on, but solution chemistry generally is much more vigorous than solid and gas reactions, and as a result, the more moist a reaction is, generally speaking, usually the easier that reaction will progress. It's not really a catalyst, it's just a set of conditions that make reactions more likely. Okay, here is another bad example. If you take bacteria and food and oxygen, and the three of those things react, you get gunk. Now, obviously, this is a bacterial reaction, not a chemical reaction. I'm making a gross overassumption, though, that bacteria are so small, right, that they cannot control their reaction rates. And so you can control the chemical reactions in bacteria the same way you can control regular chemical reactions. So if you're trying to slow this reaction down, what are some things we do in everyday life that match what collision theory would do, right? Again, the one caveat here is that bacteria reproduce. So if you create more bacteria as a product, you get more bacteria running the reaction, but let's ignore that for now. Just want to slow this reaction down. First thing you can do is make it colder, right? Remove heat, make cold. So the colder this reaction gets, the slower those reactions inside the bacteria will go, and so the slower the bacteria will digest that food. The second thing you could do is remove the oxygen gas. Again, removing gases, removing a reactant means the reaction has to stop. And when you buy food from the store, conveniently they've done this already. So when you buy sealed meat, or when you buy sealed potato chips, or sealed cheese, they've actually thrown in a layer of nitrogen gas into that food. Again, we are surrounded by nitrogen gas. It's not poisonous. But what it does do is it gets rid of the oxygen gas. And so this bacteria has trouble forming. Now, eventually, if enough time passes, some of that bacteria will find the little bits of oxygen that are still in there, and it will go further. But generally speaking, the less oxygen you have, the slower this reaction is going to go. Now, the other thing we can do that wasn't an option before is we can remove bacteria. And so there's actually a bunch of ways to do this. Again, we're saying bacteria is essentially solute here. One way to get rid of the bacteria is kind of counterintuitive, but of course we can cook it. Once food is cooked, it generally lasts longer than food that is raw. And that's because you've killed all the bacteria. Another way you can do this is if you freeze it cold enough, you can kill that bacteria. That's how they send sushi and get sushi. Clean a bacteria without actually cooking it is by cooling it down to a certain temperature. I'm unfamiliar with what that temperature was. There was talk in the 2000s about doing this another way, which is actually irradiating all meat. So this would leave the meat raw, but it would kill any bacteria by hitting it with radiation. People weren't really fond of this idea. The idea of releasing radiation into things people are going to eat makes everybody understandably queasy. I imagine they would hit this with radiation that is not long-lasting. But given my poor trust of how USDA enforces things in general, irradiating meat still sounds like a bad idea to me. You can also remove the liquid. As I said, right, you can speed any reaction up generally by having a liquid medium. Generally, reactions work much more consistently in liquids. You get rid of that liquid, actually, it makes bacteria have a really hard time getting a foothold. And there's the famous meme of a McDonald's hamburger that's been left out for a year and hasn't gone bad. People point to it and say, oh, look, it's fake. It's not real meat because it hasn't gone bad. The real issue is that McDonald's hamburger was probably cooked under intense heat, really trying to get rid of any bacteria. And then if it's left under a heat lamp for a long enough period of time, it totally dries out the bun, it totally dries out the hamburger, and even though I would not try eating that burger, it means it's really hard for the bacteria to get an obvious foothold, right? It's not going to rust or to rot out the same way that a very wet hamburger that comes off the grill is going to react. So removing the liquid, if you think about dried out foods, they tend to last a lot longer than liquidy foods just in general. One last thing here is adding salt. And we will get to salt at the end of this chapter. I'll probably forget to come back to it, but I will say for now, it's an osmosis issue with salt. The water in that bacteria is attracted to the salt, and it's going to dry those bacteria out and kill them. So, very, very salty food, okay, tends to last a lot longer. So if you think about jerky, for example, there's a reason why they made those, is adding all that salt is going to prevent the bacteria growth.